Okay, let's continue our second lecture on navigation. So, once again, reminding you that you're talking about planning for the robot. And another approach which is somewhat more accurate and better, more optimized, is what we call user navigation superclass. The examples in this chapter are all based on class derived from navigation class, which is designed for two-dimensional grid-based navigation. Each example consists of essentially the following pattern. First, we create an instance of an object derived from the navigation class, like this, and then which is passed the occupancy grid, the same concept as before. The grid has zeros and one on the map in the memory of the computer on the robot. Zero means free passage, one means obstacle, and then you can plot it. So using that kind of navigation, you have a problem like you had before. Remember, before you come like this and you go around like this, all the way to here, and then you go like this. Here, now you actually find the shortest path. Every cell which has a cost associated with it. If you want to go that direction, it may be, let's say, 0.1. Another direction, 0.5. Another direction, almost 0, 0.01. So you move where it's the cheapest. You calculate it in the memory of your path planner. So this now, the distance transform path obstacles are indicated by red cells. The background gray, here, the background gray. Intensity represents the cell distance from the goal in units of cell size as indicated by the scale of the right hand side. So, what this tells you that if you are in the white area right here, you have the longest distance from the goal. The goal is here. Goal is in pitch black, which is right there. So you basically, depending on the color of your cell, you move where you get closer to the goal. In other words, if you are here and you want to go to this cell, you cannot because of the obstacle. You cannot go to this cell. Then you come here and you see I'm far away from the goal. So it directs you to go this way and then go around, because as you can see, going from one cell to another cell, the color keeps becoming darker and darker until you get up there, which is somewhere around here. So you are moving the right direction. And then you come to a point here, and then you make assessment about the distances. You see going this way is longer than here, so you go directly. And then you go around and do the same thing here, same thing here. You go directly here and here. So the planning code keeps track of the cost for navigation, cell by cell by cell. Okay, and therefore this is much better than the one that you saw before, which was clockwise or counterclockwise, either one. And this is more like a path planning navigation. Previously, we didn't have that. So, and of course, we have used a goal of 50 and 30, which is here, initial 20 and 10, and then when you put the load map, you get this figure already. You will see it later on yourself. Okay. Another thing that you can do in your navigation planning is to keep track of the distance from where you are and where you want to be. And that, of course, is governed by this equation that you already know. If you are at x1 and y1, you want to go to x2, y2. The distance is a square root of delta x squared plus delta y squared. Okay. Or sometimes they also call it city block, also known as Manhattan distance. Okay, which is this one. So you could also use this as a definition of the distance. So this particular navigation, distance navigation, is governed by the command dx form, starting with your map. Then dx will be your distance to the goal, and you can create a plan to reach the specific goal, and then you can plot it. And figure 5.5, which is up here, actually this is the one. I beg your pardon. There is nothing for the, yeah. That's the same. This is actually distance transform path. What I told you is really relevant to section 5.2.1. So in this one, you are looking at distance to the goal, okay? And you cannot check this distance because of the obstacle, but you can move again by looking at the what the author calls navigation superclass, and the distance gets smaller and smaller, and then you keep moving darker and darker until you get to there. Okay, so this is the result of this piece of code. And you can also use a 3D plot of that navigation, which looks like this. Okay, you need to visualize it. It's a little bit difficult to do that, and you sometimes may have a discontinuity in part. Anyhow, this is just a fancy way of looking at it. It's not that exciting, unless you are doing a 3D for a flying robot. That's a different thing. Another algorithm, the D star, is extension of A star algorithm for finding minimum cost path through a graph. And if you want to learn more about graph theory, Appendix J is the place. Okay. This popular path planning algorithm is called D star, and it has a number of features that are useful for real-world application. D star generalizes the occupancy grid to a cost map, which represents the cost in a scalar value, being a non-zero value of traversing each cell in the horizontal or vertical direction. So, if you move in the horizontal, you have a horizontal cost. If you move into the vertical, is a vertical cost. If you go straight, it would be a square root of the sum of the two costs, which is less than the sum of those two. Okay, that's a straight line. Is always the shortest distance. Now, the cost of traversing cell diagonally, as I said, is c square root of 2. For cells corresponding to obstacle is infinite. So if you want to go from here, let's say you want to go from here, from this cell right here, you're in this cell, you're going to go to this cell, the cost is infinite because it's obstacle. It's the red part of the graph. So that's what it's talking about. Therefore, from here you can go to the cheapest route. DSR finds the path which minimizes the total cost of travel. Okay, almost like traveling salesman problem. I don't know if you have heard of traveling salesman problem. It is a problem of someone who is traveling with his or her own car, wants to go from city A to B to C to D, a whole bunch of cities. And it goes through the whole cycle of A through, let's say, G, 8 or 9 cities, with the minimum cost, minimum travel time. Okay, that's called traveling salesman problem. And one of my students in this course 2 years ago moved the robot in the floor of the ACE lab to go from several different designated points. So he implemented traveling salesman's algorithm on the Pioneer robot and moved with the help of ROS, robot operating system. Okay? And that actually landed him a job in Dallas. Okay? So I expect 2 years from now, all of you will be up. You got the jobs. Okay? So let's see. So in this case, you start with your map as usual. Then you go to a command called ds star, call it ds. And it goes through cell by cell, and each of them figures out the minimum cost of going from A cell I to cell I plus 1. And the DSR planning converts past occupancy grid map into cost map, which can be retrieved like this. You look at the cost of the entire path. A plan of moving the goal is generated by this. Plan and goal. Now, every cell is a graph vertex and has a cost. So, in Appendix J, as I indicated a few minutes ago, you have just enough background from graph theory. So, you can use this DSR is using graph theory to go from point A to final destination through this DSR algorithm. Every cell that the robot moves is a node on a graph. Okay, so if I take you to let's say if I take you to this is H and this is I and this is J, graphs. Okay. A graph is an abstract representation of a set of objects connected by links and depicted graphically as shown in this figure. So you want to go from point 1 to point 2 to point 3 to point 4 and 5. Here are 5 nodes of a graph, and the lines connected to them are called links. So this idea of graph theory is what has been used here. Okay. Every cell is a graph vertex and has a cost, a distance to the goal. So every cell has a price tag on it. The cost from that particular cell to the end location. So clearly, when you have a full coverage of every cell in your map, and every one of them has a cost associated with that cell, you can just compare the least expensive path and you move. Okay, that's what that is. Now, in MATLAB, this initial planning phase is quite slow and takes tens of seconds, and the number of iterations is 10,558. For that particular map you see, with the red obstacles, you saw that. Okay. And this path from an arbitrary starting point to the goal obtains like this. Now, the real D-star comes from the being able to efficiently change the cost map during the mission. In other words, having a map with all the costs associated with every cell on the map is something already available in the memory of the robot. However, you can modify this algorithm that make changes in direction and orientation of the robot in the middle of the navigation. In other words, put some additional information to be able to see what happens if I go X and Y, or I go directly, for example. So, this is actually quite a common requirement in robotics, since real sensors have a finite range and robots discover more world as it proceeds. In other words, in spite of the fact that you may have near perfect map on the memory of the robot, there may still be something happen accidentally or randomly happen en route to the goal, which you need to have enough code available on the robot to make real-time adjustment. Okay, so this modification is changing in the cost. For example, let's look at a range of Y, rectangle of 78 to 85 and a horizontal of 12 to 45. And this means you have actually right here, you have created a zone where that zone is going to be less expensive because you can go directly like that. Okay, so this dotted rectangle you see is described right here. Where we have raised the cost to 2 for a small rectangle region to simulate the path of terrain with lower traversability. This region is indicated by the white dashed rectangle in this figure. The other derivable cells have a cost of 1. The path is updated by invoking the planning. So then, instead of going like this for the original D-star, it goes like this and like that, come down. You see the difference between the two? One is going straight down immediately. The other one goes as far as possible to reduce the cost and go straight like this. And then the idea is that you will save more money by just spending this much cost, number 2 in place of 1, to being here a longer, much longer. Okay. And then this approach gives you number of iterations on MATLAB 3,178, which compares to 10,558. It's 30% of that. It's cheaper than that. Okay. So this is how you do it. Of course, then again, the author has given you a little bit of taste on graph theory here in this purple box. And going from zone to zone, you have like this, okay? and then you may go 1, 2, 3, 4 to 6, or 1, 5 to 4 to 6. Okay. What you want to avoid, 1 to 2 to 5 to 4 to 6, that's longer. Okay. Now, at this point, I want to leave the chapter for the time being and come back to it later. When I come back later, you will see that we're going to use what's called Voronoi tessellation, which you have a bunch of zones with or without obstacles in them. You go from center of one zone, equal distance between your boundary to this, and then from here you may go equal distance from here to here to here to here, and then you go from here to here and so forth. So this is what's called Voronoi. It's called Voronoi roadmap method, which you look at your map, you change it into zones like this. The zones are all going to be connected every 3 paths with 1 point, the blue dots. And then you will have cost associated or moving from zone to zone to zone. And this is how that costs are going to be going. The dark ones are the obstacles, and the whitest one are the best way you can move around. But we get to that later. Okay, so for the remaining of this session, let me go to this one of my books. This book is called, this red book right here. This book is called Fuzzy Logic and Control Software and Hardware Application. This book was published in 1993. And in fact, our publisher, Prentice Hall, informed us at the time that they were very happy because they sold 5,000 copies of this book. And for a very highly advanced book at the graduate level, you don't sell that many books. The reason that they sold that many in a short time was because Motorola at that time was in Austin. Now it's changed the name. They sold it
Google.
to another company.
Google, right?
And Motorola was coming like many other manufacturers around the world. Since 1989, 4 fuzzy chips came into market beginning. Ironically, all 4 were designed by Japanese. 2 of them, one of them was Japanese American, the other 3 in Japan. And Motorola, of course, and Intel and many others actually came around realization of manufacturing fuzzy logic chips, which essentially puts it inside the machine and mimics the approximate reasoning and decision making of a human being. Okay? It really works. Recently I gave a talk to a global international audience about the life and contributions of creator of fuzzy logic, Professor Zadeh at UC Berkeley. And about 4 years ago, I was giving a lecture to, believe it or not, to 5,000 patent examiners in US Patent Office in Washington. And I was talking about system of systems. But then, of course, I looked at what's going on in terms of fuzzy logic patents. At the time, 25,000 patents have been issued using fuzzy logic one way or the other. Okay? Which is incredible. And this book was the result of a class like this that I'm teaching in 1990s. I had about 20 students in the class, There was only one session, it was all undergrads. And every 2 students, like you are doing here, had a project to do. There were 17 chapters in the book. 6 chapters were fundamental, which I and my co-editors, Dr. Wadi and Dr. Ross, wrote. The other 12 chapters or so, or 11, 12 chapters, were all done by students. And every single chapter you see in that book, which is written by students, is Harvard related. So I'm going to walk you through a few chapters of this book. You can download it here if you don't have it, but I think I already put it on the Dropbox. So this was actually the introduction, which I wrote it, which shows background of the concept of fuzzy, and logic is two branches, fuzzy logic and predicate logic. In predicate logic, you have symbolic manipulation, you have exact reasoning, and you have probabilities. In fuzzy logic, you have symbol manipulation and numerical computation. Your reasoning is approximate, it's not exact, and you have possibility versus probability. That is now a new concept for you that you probably haven't heard from. So the possibility is like probability is between 0 and 1. However, the difference is that probability you have only 2 values, in possibility you have infinite. Okay? So, and it is its best description is that, for example, if you are a short person like me, 5'8", 5'9", and you, well, in America you are short. And you go to a tall person, which like our good old Tim Duncan here in Spurs, for 7'2" or 1 inch. So the probability, looking at one short person playing basketball against a very tall person, probability is 0. Okay, but in possibility is maybe 0.2, 0.1. So you have some chance. You may be able to get clobbered by Tim Duncan, but you may also get lucky to shoot a couple of baskets. Okay. So this is a comparison of predicate and fuzzy logic. So again, I'm not going to take you through membership function. This is something I think you should play with MATLAB toolbox. Fuzzy control is the one that I want you to do for your experiment number 3 in the lab. And the way you do it is this. Here is your robot. Here is your robot. Robot will give you sensor information. You take it to analog to digital converter. You convert the numerical values. You run it through a sequence of membership functions. You get maybe multiple values for that same initial numerical value. You may have, let's say, a distance could be short with this membership value, could be medium distance in this membership value, and far from another membership value. So you have 3 values, 3 distances for that fixed value of original sensed value. Then this is your inference engine. This is where you write your if-then rules. Okay? And then you come up with fuzzy decisions. You defuzz it. You change it back to numerical value in digital form, convert it to analog, send it to the robot. Okay? So with the help of our teaching assistant Berat and our postdoc, Dr. Benavides, will help you create this in the lab. Okay, is what you need to learn to do in the lab. Okay, and my time is up now. We will continue this after break, and that's 10 minutes.